Hi students, so now we'll go for an exercise on reduced order observer, but this time is for a MIMO system. Okay, we'll take the helicopter system. You have 8 states, 3 input for B and 5 outputs. You can see that from C. So it's a 3 and 5 out system. U1, U2, U3, Y1, Y2, Y3, Y4, and Y5. Also, we found the eigenvalue of A to know the stability, to check the stability of it. It's an unstable system, and we saw it was a type 0 system. So then we need an integrator, right? We did that last time, right? We built an integrator based on K. So we have 8 states. K, and for Ki, the remaining 3 states, which is the output state. Whatever we feed all, in type 0 system we feed all the states, but in the forward loop, you remember we only take the outputs. We feed only the outputs, whatever we want to control is a servo system, we feed it back to the output. For the state, we feed all the states, and that's the inner loop. And why it's a 3 by 3? Because those are I want to control 3 output out of 5. I have 5 outputs, but I'm interested to control only 3 of them. In our typical exercise, it's not like because I decided to track 3. In this tutorial, they want to control only 3 outputs. And because I have 3 inputs, so you have 3 rows as in 3 by 3. Your K hat vector, it has 3 lines. Why? Because simply you have 3 inputs, and this is something fundamental we all know about. And that's how we control it. Alright, so that's we did other type of control. You remember last time. You can go to the Simulink model. That's the one proposed by the MATLAB tutorial. They feed the 5 states and they control 3 of them. And what are those 5 states? We were looking at them by looking to the C measure. What are these 5 states out of 8 that they are feeding. At least we are sure they are feeding the unstable state. So this is very fundamental. You should feed them in the state feedback. Later on for the output, it's up to you, whatever you want to track. And that's what MATLAB did. You have 3 by 5 feedback matrix, so 3 by 5. Because you have 3 lines and you are feeding 5 states, which are your output actually. You are feeding all your output, but you are controlling only 3 out of them. The first 3 actually. According to this selector, we know that they are feeding the first 3. So what we did is differently, as we studied in the lecture, we feed all the state, and so to feed all the state, I should have identity matrix here. And therefore, I multiply by C to get the output and select 3, the first 3 of them, I feed them back to here, and 1 over S because I'm an integrator. All of this we done with last time, and we checked that if we don't use the role of filter in simulation, this doesn't affect your results, remember? But here we did it as of the tutorial, so just for a comparison, for sake of comparison, and we also get the same result everywhere, almost everywhere. Everywhere we get the same results. So 3 by 5 and 3 by 3. Like I'm feeding 3 states. Well, and here I tried with you in case I ignore the fact that it is a type 0 system, and I used as if it is a type 1 system, so I don't add an integrator. And in this case, I feed whatever is not in the feedback loop. So 3 of them I feed, and this state feedback is only the remaining 2. And we checked the control effort in this scenario, and we saw how high it is. Okay, so enough revision for now. What we will do now, we will design a reduced order observer for that system. I choose to go over this system and I want to design a reduced order observer for it. Okay, so I will take it here. So this is my system that I'm interested on. Alright, I can simply, if I wish, take off, because we proved last time that really this is not doing nothing in the simulation. Okay, that's it. Okay, this is my system. So now you need to design a reduced order observer. So basically, so designing a reduced order observer, we will feed, in designing an observer, you actually need to do what? You need to get the output, right, which is Y, and the input, which is U. Both of those to the reduced order observer. Let's say you have full order observer for now. So if it is full order observer, so you observe all the state and you get X tilde, which is all the states are observed, and here all the states they go here. So see, you are not feeding anymore now from here, because you don't have access to the states. You need to observe them. So you from the measured output that you know, always Y is measured, is known, and U is your control effort, is known. Based on them, you calculate, you estimate, based on the model. So here you have ABC, how accurate it is. So you observe all the states and you feed them back, and that's what will be your full order observer. That's how it will look like. So if it is a reduced order observer, so you just, in that case, from Y, you are measuring Y. Because it's reduced order observer, you don't measure all the states. You have access to some of the state, those you can measure, and some others you don't have access to them, so those you cannot measure. And this is very important. Like here I have 8 states, x1 up to x8. So I know that I can measure 5 of them, because that's your Y. Y is actually 5 of those states. So I can measure 5 of them, and 3 I cannot measure. So I'm considering my X as 5 states which I can measure, 5 measured states. So those are the output state. So then the output state are the measured state, and the remaining 3 states are unmeasured states. And therefore your reduced order observer is for the unmeasured state. So that's basically what it's about. So you need to figure out what are the measured state, what are the unmeasured state you have, and you will feed, so you will design your reduced order observer based on the unmeasured state. Because you have 5 outputs, and this is something not new, of course, you know. Those are the measured state. So if you look at them, here you go. So x4, x7, x8, x3, and x6 are measured state, are the measured state. Those are your, actually it's your Y. You see, it's Y1 up to your Y5. According to the state, the matrix C, we found them last time. Okay, that's your C measure. Okay, so then those are the measured state, and the remaining are the unmeasured state. Like x1, it's unmeasured, x2 is unmeasured, x4 is measured, x5 is unmeasured, 6, 7, 8. So those are the unmeasured state. So now you need to arrange your matrix in a way you put the measured first and the unmeasured after. Okay, so I will go first step by step in designing a full order observer. So don't go, if you wish, directly to a full state to minimum order observer. You can get trained with a full order observer. So I will do a full order observer with state feedback. So basically what we are doing here, I have my output y, which is measured, I know them. I have my control input u. I get x tilde, which is the 8 state, are all observed now. I'm observing all the state, I'm feeding them back, and I'm doing regulation, okay? Regulation. So this is 0, not servo design. So maybe you have two unknowns we need to find, k, and we know it's a place, a, b, and then your desired closed loop pole for the system. And here you have L for the observer, Lemberger, or KE we call it in the lecture. And this is place A transpose, because it's a real matrix, C transpose, also your desired transpose. So here you get your L. And of course you should know that K is, as in dimension, you can know it, right? You have 3 inputs, so U1, U2, U3, and you have 8 state, so X1 up to X8. So then it is 3 line, 8 column vector. And what about L? What about L? A transpose, C transpose, here your desired closed loop transpose, and L dimension. L is, you have, because it's transpose, well, you usually have 5. Here is the state, usually here is the state, as here, analogy by analogy with K, here is the state, and you should have 8 state, but because it's transpose, your state are here, X1 up to X8, and here is what you should have here. Is it U? Is it the input? Or what? Actually it's the output. So Y1, Y2, Y3, Y4, and Y5. So it is 5, 8 line, 5 column. So a simple way to check it is what? Let's see here. Here you have 8 by 8 state, and you have 3 by 8 state for 3 by 8 dimension for B, right? B is 8 by 3, so it's actually 8 times 3. So you have 8 by 8 times 8 times by 3 AB, so it gives you K, and here you have 8, of course. So it gives you K 3, 8, right? 3, 8. So now here what you have, 8 by 8, even if transpose, and for C transpose is what? C is 5, 8, so 8, 5. So then it is 8, 5. And here you have 8, so then you should have 5, 8. But because it's a transpose, so then instead of 5, 8, you'll be having 8, 5, because you have the transpose. So then you don't forget. 8 refer to the number of state, and 5 refer to the number of outputs. So then that's the size of your L. Okay. So I'm checking the controllability. If it's full state controllable, I'm checking the eigenvalue, we know. Well, Here, the way I find K using LQR, we didn't, up to now, we didn't explain introduction to optimal control, LQR. So then, but you can do it simply this way. You can choose a, as we did, like place A, B, as we know up to now. And you can choose your pole location, the place you want. So you see here, I have this, I was trying another pole location. Well, optimal control, it's much easier because you don't need actually to get a desired pole. You just, it will converge by iteration to your goal. This will explain in next chapter, next section if you wish. Also, you need to check the observability and design your observer. That's how you go with your observer. A transpose, C transpose, you see, and your desired observer dynamics. So it's as easy as that. So, and transpose. Don't forget the transpose of it. Okay. Also, I didn't do it this way. I'm using optimal control. It's fine. So also you are invited to check the stability of the state feedback and the observer as a whole system. So this is a closed loop system, including the observer and the state. So this is something you can do. And that's it. You know L and you know K, so then it's alright. So you can, I run my system. Let's check the dimension if you wish for L and K. Actually, I'm not, okay, let me check K first. See, size of K. 3 line, 8 columns. And let's look to L. Here is L. And what's the size of L? This is for the observer. It is 8 line, 5 columns. So now let's check it on Simulink. I basically, here is your K that you found, and here is your L, right? So I did LQR. It's not well. You can do it as a place, using place as we normally do. But here I'm using optimal control, which will be introduced in our last section for state space design. But for now, here you go. So nothing new. This is your X, because here I put actually identity, so I get X out for the purpose of comparison. So X with my observer, full observer. So I'll be able, as we did in previous exercises, when we design a full state observer and we compared X to X tilde. So here I'm doing the same. So in this scope, I'm comparing X1 with X1 tilde and X2 with X2 tilde, for example, etc. 3 and 4, 5, 6, 7 and 8. All the state, for example, 7 and 7 tilde, 8 and 8 tilde. So we are comparing all together based on our LQR control, optimal control. So we can do it using place, right? And nothing new. So here is X and here is X tilde, getting it out from here. And here you go with all. You can see that's the output of the optimal control. Maybe you can make it better. Actually, you should think a way to make it better, because you see you have difference between your X actually and X tilde. So you should think about a better combination to have a better. Maybe you can find a way using control system tuner app. Okay, in a way you can make sure that X is converged to X tilde. So you see, if you want to use like just a short comparison between LQR and place, so you find that LQR is better, is giving better result. But let me just comment the LQR way and find K and keep place AB with the design goal with closed loop point position. And and same for here. Use L. Okay, so if I run it, so let's see. Okay, so these are my result. See now, looks like up to 1000. So it's not really a good design goal with an observer that I took. So that's why optimal control is better. I mean, it seems like they are following each other well, but with, if you want to keep here it oscillating a lot. So your design goal influence your state, as you know, your K influence your state. So then they can follow each other, but with some minor things at the beginning. So here you see they are perfectly following each other, but look, it goes up to 3000. So then up to you, the designer, which, so it seems like there is full mismatch, full matching between x and x tilde, except for x1, a bit changed, but at the end the signal is high. So you can keep this, or using LQR you can try to have different observer location or different feedback location. You can even have different one and try it. Okay, that's for the full order observer, but we want to do, remember, minimum. You want to design a minimum order observer. As you know, how to design a reduced order observer is basically it returns to find the separation matrix, or if you wish, the partitioned state and output equations, which is AAA, AAB, ABA, ABB, BA, BB, C. If you have C, so you need to have maybe C1, C2. Once you found them, that's it, that's all. Because once you have them, you need to find KE, A hat, B hat, and F hat. And KE is related to ABB, AAB, right? And A hat, B hat, F hat is function of. So then everything it returns to do this partitioned state, in which you have first the measurable and second the unmeasurable states. And those are very easy because this is rearrangement of the matrix, nothing more. Like in your case, in our exercise, if you go to our exercise, so then we need to build the reduced order observer. It returns to finding the partitioned state. So then you have the measured state and the unmeasured state. So you know your x, so x hat, if you wish, is composed this time from measured and unmeasured state. So we start by the measured state always. So you start by x4, x7, x8, alright, x3 and x6. Then the remaining are x1, x2 and x5. So those are hat because this will be observed. So we design a reduced order observer or minimum order observer for those states. Okay, so yeah, so it returns to rearrange the matrix, nothing more. Also, before, it's a good practice before building the minimum order observer to check the minimum order observability. As we always doing, we check the complete observability, so it's fully observable. In order to design a full order observer, we need to have a minimum order observer. So then we can check the minimum order observability before finding the LM mean. right? Or we call it in the lecture KE. Before finding the minimum Lamberger mean, we check the minimum order observability, or we check if it's partially observable. It should be partially observable. At least those three states should be observed. Okay, so I'm not caring about full order observer because I'm not designing full order observer. If it is full order observer, then fine. So just how to check if it's full order observer or not, that's X. You can take X, not X hat, you can take X, which is X1 to X8. You have 8 state. Um, so you know X dot equal AX plus BU, Y equal CX plus DU. We know how many input and output we have, etc. So then how to find the observability? Observability matrix is obs of A, C, and then you find the rank of them should equal to the length of the states should be equal to 8. So then you are full order observer. If the rank equal 8 means you are full order observer. If you are full order observer, that means you are partially order observer. That means you can design a minimum order observer, of course. But at least you need to make sure you have partially observable system, so you can observe those states. So if you're able to observe them, so you can design LMIN. Well, how to find what are the matrices that I need to check in order to check the minimum order observability? To know, we first need to partition the states into AAA, AB, AAB, ABB, etc. Right? So how to do that? It is very simple. You need to rearrange your state equation and your output equation. Well, let's start with a simple example. Instead of having 8 states, maybe assuming I have 5 states only, just for the sake of demonstration for you. Assuming I have 5 states, uh, x1, x2, x3, x4, and x5, and in which I have the second and the fourth, just assuming for the sake of demonstration, the second and fourth are measurable, alright, and all the others are unmeasurables. So then I can, in that case, you can have x hat, you rearrange it by the following: xa and xb, right? Xa is the measured, so which is x2 and x4, and then x1, x3, and x5. Those will be the observed state, if you wish. Okay. So the measured first, remember, always the measure first. So if this is in which you have A, matrix A, so taking it as A11, A12, A13, 4, etc. So here you go, I write all the 5 states for the matrix A offline: x1, x2, x3, x4, and x5. Same x1, x2, x3, x4, and x5. So you have 5 states, and how many input you have? u1 and u2. You can know that from looking to B. In this example, how many output I have? In this particular example, just for the sake of demo, I also have 2 output, y1 and y2. From C, I know how many output I have. Okay, so then I need to arrange it in a way. I have x2 and x4 are my measured state, so those are, say, xa, and those are xb. So then let's start by arranging B. So B, if I want to arrange it, remember here is x1, x2, x3, x4, and x5. So if I want to rearrange B, okay, so how B will be? So then B, if rearranged as B hat, will be,
right, will be having x2, x4, then x1, x3, and x5. So then it will be b21, because this is x2, b21 and b22. Then later after it x4, so then b41 and b42. Then remaining b11, b12, b31, b32, b51, b52, and here is your BB matrix, and here is your BA matrix. If you need BA and BB, so now we know BA, we know BB, we know XA, we know XB. What about C? Let's start by C, because and keep the A to the end. So that's how B is rearranged. Okay, what about C? How C will be rearranged? Also very simple. When you look at C, here you go. When you look at C, so you have x1, x2, x3, x4, and x5. So then you need to start by x2, x4, then x1, x3, x5. So how it will be then? If you want to start by x2, then c12, c22, x4 is c14, c24, then c11, c21, c13, c23, c15, c25. Alright, so then this is C hat. If you wish, it is divided into C known and C unknown. Alright, like CA and C measurable and C unmeasurable. Okay, the measurable states are 2 and 4. This was my assumption. So I'm designing a reduced order observer for the unmeasurable state, for the 1, 3, and 5. Okay, remaining is the state XA. Also should not be that hard. Following same methodology, you can get a hat. So also a hat, it is arranged in a way x2. Okay, you start by x2, then x4, then x1, x3, then x5. So the specific thing about the state matrix A is that x in the rows and in the columns. So then you should have mutation in rows and in columns. Like here, for example, B, you have mutation in rows. C, you have mutation in columns. But A, you have both. So now x2 here and x4 here, and then x1, x3, and then x5. So then just you need to pay a bit attention when you are building the matrix A. Okay, and therefore once you do that, you will get a hat. Alright, so therefore a hat is a22, okay, a24, a21. Let me show both to you, so then you can compare. So then a22, a24, a21, a23, and a25. Okay, then for 4, a42, a44, a41, A for 3, and A for 5. Then A12, A14, A11, A13, and 15. Then for x3 is A32, A32 because x2 and x3, A34, A31, A33, A35, and okay, and move up. Okay, and the last one, which you can see it here, but you need to arrange it. You need to arrange it by having x2 first. So then A52, then A54, because A54, then A51, which is remaining to x1, and A53, and A55 belongs to x5. So then that's A hat. Okay, for A hat, it is the following. So then, now if we ask about um, AAA, AAB, ABA, and ABB matrices, you know them. So this is your A hat. After rearranged it, the measurable and the unmeasurable after. So this is very important, okay? And that's how we arrange it. Once it's done, so now if I want to go to the lecture, it is in here. Here it was explained. So now you have them. You have AAA, AAB. You have CCA, if you wish CB. You have BA and BB. So you can find KE or L mean. I myself call it L mean. Alright. You can find it, and you can find A hat, B hat, and C hat. So this is just, I will copy paste it to my exercise. Okay, let's now find L mean, right? So L minimum matrix gain Lemberger as L. This is place or acre, place or acre. Okay, place of what? Of ABB transpose, because it's assuming serial, AAB transpose for the observer, for the minimum order observer. You need to find what? You need to find the observer dynamics that you are looking for. It's recommended to be faster than the feedback, the state feedback dynamics, the closed loop dynamics of the system. And all is transposed. Before finding it, verify the observability. Okay, so the observability, if you wish, the minimum observable matrix, it is observe of A, AB, ABB, AAB, and to have this minimum order observer, this two matrix should be of rank what? Should be, to be like to design minimum order observer, the rank of minimum order observer should be equal to what? To the length of the unmeasurable state, which is 3 in this case, in our example, right? Whatever we took in our example. So then it's equal to the length of the unmeasurable state. Like here you have x1, x3, and x5. And this demo, okay? Remember, we are working with the helicopter at the end, not with the system which has 5 states. I'm working with the helicopter, okay? So it returns to find them. Once you find now we just found L-min, so remaining A hat, B hat, F hat are function of L-min or KE in this case, and BB, AAB, AAB, ABB, all of those are found. Alright, so then let's go based on it. Before I go into MATLAB, so in MATLAB we will build the matrices first, because it's the first step, building the matrices. Once we build the matrix, we compute the minimum order observer gain, so we can know our minimum order observer. Just before going to there, I want to go one step, showing you iteratively how I can find a hat in MATLAB. So in MATLAB I have A, and I know my measurable and unmeasurable state, assuming in this case I'm saying x2 and x4 are measurable. So how to do? I do a two mutation in two step. The first one, I go from A maybe to a new A hat or whatever, a new, if I can call it a new initial and a new final. In the first step I do the following. Maybe I do imitation of A21 and then A41, like, okay, I do mutation as B, like A21. Okay, this is, I take that row and I push it up, and I take that row and I push it to here, and this will be our first mutation. So then I take A21, A22, I'll do offline, okay? So as you can see, I did it offline. So this matrix, the new matrix A, is obtained by mutating this row x2 up to here, up to the first row, and the first row to the second row, and then I get this way. Then the second mutation you need to do is to push here to the first column and push here to the second column. So then you have two mutation. Once you do this mutation, you will end up having your final A hat. So compare it when you mutate the second column to the first and the fourth column to the second, you will end up having A hat. Okay, so that's what I did in MATLAB to find my matrices. I find my matrices, I demonstrate the minimum order observability, so it is a rank of 3, right? A rank of 3. But once I done, I do it in Simulink. Yeah. So let's go to our exercise. In our exercise, you have 3 unmeasurable states, but I have 1, 2, 3, 4, 5 measurable states, not only 2. So I have 5 measurable states in our helicopter case, which are x4, 7, 8, 3, 6. So then in MATLAB, simply that's how to go with, for example, B new and C new. So you start by 4, 7, 8, 3, 6, and the remaining are 1, 2, and 5 are the unmeasurable state, right? So 1, 2, and 5 are the unmeasurable state. 47836 125, 47836 125, 47836 125 for B as well. So then you get C new and B new, and pay attention how I did the mutation. Well, this is nothing than math, okay? So you understand it. It's an algebra. So then in MATLAB, make sure here you are mutating in C. What do we mutate in C? In C we mutate the column, and in B we mutate the rows. That's why it is like this. Then for E, as I told you, I told you have two transformation. First, I mutate rows. Then second, I mutate columns. So then I get A new. A or yeah. A. So then from it you come here and you get your AAA, also CA and CB, as you saw in here. Also for C, I can have CA and CB. And that's it. That's all what I did. Okay. You can look at it again in MATLAB. That's basically what I did. Good. I can check the minimum observability. Once it is, so I design my minimum order observer based on my minimum observer dynamics, right? And that's it. So I go to Simulink, and in Simulink we already showed to you the first step, which was full order observer. We designed a full order observer, and we compared uh, x1 x1 with x1 tilde, x2 with x2 tilde, etc. And here is a full order observer, or could be full state feedback. If you want to do, you can also have k here and do full state feedback, but it's a regulation, okay, because here I have 0. You can do this is you are good on. All right, so this is a full order observer, so I'm observing all the states. Why I want to observe them if some of them I'm able to measure and I have a sheep sensor, etc. So I do a minimum order observer, and here is nothing, just I'm putting well, here I put b hat, actually, I didn't put ba minus l minimum times a hat, as I show you. So you have two different ways. As the previous exercise we did it, and here I just show it to you using b hat. So we saw that in the lecture. You can have b hat or rearrange it in this way, having aba minus keaa, and both are fine. Last time I showed to you this, so now I decided to show you this. It's the same, just rearrangement of the block diagram. Right, and you see it is very similar to a minimum to a CISO system. Nothing will change. Okay, and then of course you have better accuracy for a minimum order observer compared to full order observer. Less error you will be having. Why? Because here some of the state are measured, are the exact state, so you have no differences in between them. Like here, like whatever here is x1 and x2 is exactly the same, because those are measured state. Also x3 and x4 are exactly the same. Alright, so all of those are measured state. Actually, sorry, x4, x7, x8, yeah, well, yeah, the first at the end, 1, 2, 3, 4, the first 5 state, 1, 2, 3, 4, 5 state uh, are the measured state. So yeah, So just to be correct, those are not x1 x2. Just to be correct, here are, they should be what? They should be x4 x7 x8 x3 x6. Okay, x4 and x7. Okay, so those are the measured states. So I'm comparing x4 with x4 tilde, but it's the measured state, it's the same. And that's why, because I'm not designing a reduced order observer for those state, for those measured states. So that's why you see no difference. And 8 and 3 and 6 and x6, x1, you start see a bit difference, but still better than the other case. So x1, x2 and x5, x2 and x5, still better than a reduced order of a full order observer. Okay. Of course, here you expect no difference. Here you expect no difference. In x6 you expect no difference. That's x6. Okay, you expect no difference. In x1, here is x1 as I said, and x1 tilde. So you see a bit difference. Okay, especially a tilde at the beginning, then it will depends on your dynamics that you took. And a good comparison is to compare it with the full order observer. Here actually I'm having x1 x2 x3 x4, they are arranged by order. Here I rearrange them, so that's why because I just copy paste my scope, I get it this way. But you know, you should name it differently now, because you rearrange the state. Look to the helicopter, you have the new A, B, C, and I have initial condition because I have zero regulation. So you rearrange your matrices in a way. Remember, your state start by x4 x7. Your state on the full order, on the minimum order observer, that's the meaning of minimum order observer. You start first by the measurable states, okay, and you end by the unmeasurable states. So you rearrange your system in new A, new B, new C if you wish, and new D. But here I still have the old system, so I didn't arrange it. So then the first state is x1. Whatever it's measurable or unmeasurable, they are by order. Okay. If you want to compare, for example, x2, here you have x2, last one is x2 and x5. If I want to compare it here, here is x2. Wow, very cool. So let's see. Okay, if you look at, I said this is x2 here, and here is x2. So you have x2 and x2 tilde. Here you have x2 and x2 tilde. x2 is the yellow one. Okay, x tilde, x2 tilde is the blue one. That's the observed state. Look to the observed state in the full order observer, and for the minimum order observer. So it is more accurate for the minimum order observer. It returns in less than 1 second, less than 0.5 second, to converge to x2. So then my measurement, my observation is very accurate, as my real state, which I don't know it. Here in simulation I have it, but here it takes time to reach it. See, that's why minimum order observer is better, because it's based on more measured data. Okay, but the full order observer is not. Even when you go to the implementation, you should not forget that your A, B, C, and D matrices are not accurate. Your model is not accurate, so you'll have more even uh, divergence. Or yeah, good. So yeah, that's it. That's the minimum order observer, um, and we know how we did the partition now in here. Is there anything else I want to say? No, if you wish you can simply redo what we did before, when we designed a servo design for it. So that's one of the things just I copied from previous exercises when we did servo design for the helicopter, so you can refer back to it. I'm feeding the state, and here I will be having 3 by 3. And you why here 3 by 3? Because you have 3 output. You are feeding 3 output in here, and you have 3 input. So then you have 3 by 3. Alright, so this is explained a lot before. Okay, so you can go back to it. It is, of course, it's here. You have 8 state, and here is your ki, okay, which is 3 by 3. 3 input and 3 output you want to track. And 3 by 8 is the state, because you have 3 again input and 8 states. And of course, because it's type 0, 1 over s. So all of those we explained before. So I will do the same now, but not based on my state, based on the minimum order observer state. So in the sense, I need the 8 states, but I can measure 5 of them. So those who can measure, I feed them, I feed the exact state, not as observed, and the remaining 3 I observe them. Because in simulation you can always consider I have my state, but in implementation you may don't have. So how to feed them, how to do state feedback, how to feed your state if you don't have them, you need to measure them. So I'm able to measure 5, so then I need to observe 3. So I designed a minimum order observer, which is the same observer we did here. Okay, but now I did a servo design. You can, as I said, you can even here do a feedback, do a state feedback. So you can have here again k and feed the state, the observed state, the minimum order observed state, because the other state only I'm observing 3 states out of 8. The remaining 5 I'm measuring them. I have sensors to measure them. So that's the minimum order observer. As always, this is the output. You see C new. I'm using C new. You should pay attention. So here, because repartitioned your state, and in here A new, B new in case it is needed. Okay. Identity, because I want to take out the state here, so be able to do a comparison. So again, here are not x1, x2. So pay attention. Those are not x1, x2. Those are x4, x7, x8, x3, x6, x1, x2, and x5 by that order. So because I copied it from other places, so I'm keeping them x1, but it's not. Okay, so I did, so this 3 by 8 and this 3 by 3, you can do it using minimum or using some closed loop pole location, and then you can get your k, and from it, as we did before, from it you can divide them into k and ki, or you can simply using control system tuner app to design your 3 by 3 and 3 by 8 matrices, but not for LMIN. LMIN you cannot do it using control system tuner app. So this is you need to do by fixing an observer dynamics. And look to what I obtained, similar to what we had in here. So see, I have my exact same result. Here it's based on a minimum order observer. here is based as if I have access to all the states, which actually not the case in a real practice. Okay, so what are the observer dynamics you want to take is up to you. So it's up to you. Like look here what I take. Actually, I first, a good practice to look to your eigen of A, as we did before. So always eigen of A. So you look to your state, and then you move them to another dynamics, and that's to find K. So I have -10, -2, etc. So maybe I decided uh, to have this dynamics. Okay, so then this my dynamic of my state. So I'm shifting my pole to a closed loop pole location, so closed loop dynamics, which is at this location. I decided to have my 8 state at this location, so I'm changing them from this open dynamics to this location, so I find my K, and this is the K. In here I'm not taking the integrator into consideration. Okay, so this is, if you wish, the K of to pay attention, this is the K if I'm doing like feeding a state here. This is the K if I'm having a state feedback for a regulation, U equal minus Kx, not for servo design. For servo design, you need to add more closed loop pole, taking into consideration the integrator dynamics. So then you need to add 3 more closed loop pole, because you have 3, you are feeding 3 output. But I didn't add here 3 more poles, because I'm assuming here I'm doing state feedback. Anyway, so controlling those two gain, I'm doing them using, as I did before, using control system tuner app, in which I simply said I want to track my step, my three signals here. So yeah, okay, I'm checking the observability. I designed a full order observer first. I can check the stability of the state based observer, so to observer and the feedback loop, so I can check the dynamic, the stability of the closed loop. So you see here I tried different dynamics, -20, -20, -20. For a good comparison, you should actually, if this is the dynamic of the observer, you use the same dynamic for the minimum observer, like -4, -6, -15. Maybe you use -4, -6, -15, so you can do a comparison, a fair comparison, because you keep the same dynamics for the minimum order observer and the full order observer. Okay, yeah, that's it. But so that's state 1, state 2. Well, it is not like that. It's not like by order. If you do it, just MATLAB will take it. Just imagine you have a poles, and just you are throwing them on the S plane. Just you are throwing them in the S plane. Okay, it doesn't matter which will come first. At the end, that's the observability dynamics. Observer dynamics. Dynamics of the observer you designed. So then the G or min, the minimum order observer dynamics that I choose, maybe I choose -4, -6, -15. Okay, as an observer dynamics. So then I compare with my minimum order observer. Alright, or I can do LQR to find my Lmin optimal control, but this is I didn't explain yet. You can do yourself. That's it. That's it. As simple as that. Here I did some stability verification by looking to eigen of a tilde. You can figure out a tilde in the lecture. We were talking about it. A minus bk, here's the minimum order observer dynamics. Okay, that's it. That's everything about this exercise. Maybe here it's a nice paper. We did much better in here, but you can look at it for your own purpose if you wish. Let me check if that's the one. No, that's this one. I want you to go over this one. It's a nice paper, very simple. We did more complicated stuff. You can go over it. Okay. So yeah, and ours is much more complicated than theirs. So here, very simple system. 2 output, 1 input. Like your maybe inverted pendulum or so. Here is a full order observer dynamics, and here's a minimum observer dynamics. Okay, you have 2 poles at -10 and -11. You usually you take them, like if you want to reflect back in here, because you are taking GO -1, -2, -3. Well, we recommend usually, if you want a good design for GO, starting by -11 maybe, and then because you have 8, so then if you wish -12, -13, up to having 8 of them. Why -11? Because your eye of A start at -10 something, so then you say, so you see it -10.4, so then start at -11. And for the GO min, for a fair comparison, GO min, so then -11, -12, and -13. So take this as a dynamic for GO, this is a dynamic for the minimum order observer, and compare them. Of course, you will find the reduced order observer, minimum order observer is better. Good, that's it for this exercise.